Welcome to your first electrochemistry video. I'm going to try to finish this whole unit within 4 to 5 videos, so let's just get started on the first one. Let's begin with a redox review. This is from a real AP test. Why don't you see if you can answer this without my help? So go ahead and pause, try it out. Welcome back if you actually paused. If you didn't, shame on you. Pause. Do it. Okay, so we have a copper penny reacting with silver fluoride. I'm going to write my reaction. Copper plus silver fluoride reacts to form, I know it's probably single replacement because I only have 3 different things here. So I'll have silver hanging out by itself now. And then copper and fluorine. Well, I don't know what kind of copper this is. Is it copper 1, copper 2, copper 3? I don't even know. I have no idea. But it actually doesn't really matter. So we're just going to kind of leave it like that and we'll see if we can figure it out. What we need to do now is figure out what their charges are before and after. If I have something hanging out by itself, what is its charge? 0. Okay, well, I always know the charge on fluorine. What's that? -1. And if this whole thing is going to have a charge of 0, what would silver's charge be? It's got to be +1 to balance that out. Okay, you know what? As it is right now, I don't even need to deal with copper. I've already figured out the whole problem, which is pretty cool. Look at silver. Did silver gain electrons or lose electrons? Silver gained electrons. It became less positive. So, well, that's cool. If it gained electrons, let's go back to our old saying. Actually, this is my old saying. It's oil rig. Oxidation is losing, reduction is gaining. I think you guys might have used Leo says GER. Losing electrons, oxidation, gaining electrons, reduction. Whatever works. So if it gained electrons, it has been reduced. Well, let's just make sure that this makes sense. If something is reduced, something else must have been oxidized. Let's check if copper was oxidized. I know fluorine's charge must be -1. And in order to balance that out, copper is going to have some sort of positive charge. See, I don't know if it's CuF2 or just CuF or whatever, but it's going to have some sort of positive charge. And I know if it started off with a charge of 0 and it ended up with a positive charge, what must copper have done? It must have lost electrons because it became more positive. So if it lost electrons, it was oxidized. Well, we still haven't answered the question though. They want to know what was the oxidizing agent. Now, you're probably going, oh man, this is that weird thing, isn't it? Yes, it is that weird thing. If something was reduced, that means it was the oxidizing agent. It is the agent that made oxidizing happen. If something is reduced, something else must be oxidized. If something is oxidized, that means it was the reducing agent. Okay, so our answer to this then, what was the oxidizing agent? That would be good old silver. All right, there's our quick review. Here are the definitions again. So oxidation is the loss of electrons. Losing is oxidation. Reduction is, oh wait, I'm switching the 2 different sayings. Gaining electrons is reduction. I always liked oil rig myself. Oxidation is losing, reduction is gaining. Whatever works for you is fine. You just need to know, though, that the agent naming system is just the opposite. So if something was oxidized, it is the reducing agent. If something is reduced, it's the oxidizing agent. Annoying, right? I know. Okay, remember that oxidation and reduction reactions can be acidic or basic, and that determines how we go about balancing them. If you would like a review on balancing these types of reactions, let me know at some time and I will help you out. You have a new equation that you're going to need to know. It's I equals Q over T. You need to know what each of these variables represents. Let's start off with our definition of electric current. Electric current is the amount of charge that passes through the cross-sectional area of a medium per second. In other words, let's say you have like a tube and you take a cross-section of it. So you get a saw and you cut it like that. Right here. You cut that piece out and you open it up and you look down the center of the tube. This is a cross-sectional area. The amount of charge that passes through that section is the electrical current. So it's actually charge per time, which is here. Charge is Q, measured in coulombs, per time, measured in seconds. And that gives you amperes. This is a typo here. Get rid of that. So amperes, which is abbreviated as the letter A. So we know amperes are equal to coulombs per second. I equals Q over T. Current equals charge over time. Something else that's useful, which is not actually in the equation, but we're going to use it for different conversions, is Faraday's constant. 1 Faraday is equal to 96,500 coulombs per mole of electrons. This is a conversion factor. It's a very useful one. And we're going to use it in the following example problem. So just keep it in the back of your mind. So how much charge passes through the cross-section of a wire that is carrying 0.987 amperes of current for 12.3 minutes? Charge. What letter is represented or is representing charge in this unit? Q. So why don't you do this without me? Go ahead and pause and do this problem. Welcome back, those of you who actually paused. We know I is equal to Q over T. So I could say 0.987 amperes is equal to Q over T. 12.3 minutes. Wait a second. We don't want minutes. We want seconds. So multiply that times 60. And you're going to end up with a Q equal to 728 coulombs. Remember, we want to pay attention to sig figs, and our given numbers are 0.987, that's 3 sig figs, and 12.3, also 3 sig figs. So there's our answer. Don't forget your units, those are worth something. Now, how many moles of electrons pass through the cross-section? Moles of electrons. When you see something asking you about moles of electrons, your brain should go, ooh, Faraday's constant. Faraday's constant. So what I want you to do now is look constant. Look on the previous slide, find Faraday's constant, and use your answer from the previous problem to find moles of electrons. Do it without me. Go ahead and pause and try it out. All right, welcome back. Let's see how you did. 728 coulombs. And I know 1 mole of electrons can be found for every 96,500 coulombs, which should give you the answer which was provided, 7.54 times 10 to the negative third, still 3 sig figs. Moles of electrons. If you just wrote the number and you didn't write moles of electrons, I'm sorry to tell you this, but you didn't get full credit. You need those units. Okay, so let's try a slightly more complicated electrical current problem. Down here, this is the flow chart that we're going to use. We're going to start with current in amperes and time. Well, let's see. Okay, where's our current in amperes? There it is. And our time, 1 hour. And we're figuring out the number of grams of aluminum produced. So we're basically shooting an electrical current for an hour through some molten aluminum chloride, and solid aluminum is going to pop out of it. We want to know how much. In order to actually have space to do this problem, let me just erase the answer. And all right, here we go. So first, well, I have current and time. What can I solve for with that? I can solve for charge. So I know 10, whoops, that's funky. 10 amperes is equal to Q over 1 hour. Well, I don't want hours. I want seconds. So you convert that, 3,600 seconds, and you'll end up with a Q of 36,000, right? Yeah, times 10. What is Q measured in? Coulombs. Okay, so we've gone from here to here. Check. Now we need to go from quantity of charge in coulombs to moles of electrons using Faraday's constant. Okay, well we just did that. 1 mole of electrons per every 96,500 coulombs. Okay, so that's that done. Now we want to go from moles of electrons to moles of substance oxidized or reduced. Ooh, we haven't done that. So here's the trick. For this type of conversion, you need the half reaction. So think back into the past. We need to write a half reaction for aluminum. Aluminum started off as aluminum chloride. So in aluminum chloride, what was aluminum's charge? +3. And I know what ends up becoming solid aluminum. That's what they're telling us. Calculate the number of grams of aluminum produced. So just straight up aluminum. Now we have to figure out where the electrons go. Did we add 3 electrons to the cation, or does it get added up on the end? Where do we put the 3 electrons? They go right here. You put them in there, that charge cancels out, you ended up with a neutral aluminum atom. And hey, look at that. We now have a balanced equation that tells us the relationship between moles of electrons and what's being produced. I'm going to use that over here. For every 3 moles of electrons, I have 1 mole of aluminum. Okay, check. Cool. Now I want to convert moles of aluminum into grams of aluminum, and we've done that before many times. Use your periodic table. 1 mole of aluminum should be about 27 grams. And if you multiply this out, you should get the magic number of 3.36 grams of aluminum. So make sure you know this flowchart. Make sure you know the different tools that are available to you so that you can do a problem like this if it shows up on your tests. Let's talk about spontaneous redox reactions. So think back to the most recent unit. Spontaneous means what? It means it'll happen all on its own without any extra outside force, work, energy, whatever. It just happens. We also call that thermodynamically favored process. Both of those terms work. You might see, I'm not sure which one you'll see, I believe it'll be thermodynamically favored process on your AP test, but don't be surprised if spontaneous shows up too. So what we have here is we have a strip of zinc placed into a solution containing copper ions. It really doesn't matter what the solution is. It could be copper sulfate, it could be copper nitrate, it could be, I don't know, copper fluoride. It doesn't matter as long as it's just got copper and whatever other ion is in solution doesn't interfere with your zinc. So we have a bunch of copper floating around. Here's a zoomed in version. And notice how in our equation here, copper is going to want to gain electrons, while zinc is actually going to lose electrons. 2, to be exact. So what will happen is one of these coppers will come up here and it'll bump into that strip of zinc, and that zinc will be like, hey, you want these electrons? And that copper will be like, yeah, sure, why not? And it'll take them, and what will happen is that zinc ion will pop off into solution. Bloop. Oops. I wanted an arrow there. Bloop. And it'll leave solid copper behind. And it'll coat this strip of zinc. And a lot of that zinc will actually disappear. This strip will become smaller and smaller as we have more and more zinc in solution, and it'll get covered in copper, and eventually there will be too much copper on there and it'll all just kind of like fall off onto the bottom, and it'll look something like this. So here we had a strip of zinc. This is what it looked like originally, and then this is copper. That's all over it. And those copper ions, they coat it. There's actually zinc now floating around in solution, zinc ions floating around. And this is solid copper. Solid copper. So that is our very basic introduction to electrochemistry.